As mentioned previously, in this part of the lecture, we will look at two more examples of acid-base titrations, and then we'll summarize by comparing the four examples that we've covered in part one and in this part two. So let's start out by looking at example 3. Here we have a strong base, KOH, titrated by a strong acid, nitric acid. And let's read the problem. A student finds that it takes 15.81 milliliters of 0.14 molar nitric acid to titrate 20 milliliters of a solution of potassium hydroxide to the equivalence point. We need to use this information to determine the molarity of the 20 milliliter sample of potassium hydroxide. So here we have the nitric acid in the burette. We know its concentration. We know how much was needed to reach the equivalence point. There was 20 milliliters of potassium hydroxide in the flask to start with. When the titration's done, we have enough information to calculate the molarity of the potassium hydroxide. So what's familiar or different about this titration? Now, like example 1, this titration also involves a strong acid, strong base reaction. But in this case, the strong acid is nitric acid, and the strong base is potassium hydroxide. Now, unlike example 1, the strong acid is now the titrant, and the strong base is in the flask. And like example 1, we are attempting to determine the concentration of the solution in the flask. So let's work through what hopefully is becoming a familiar routine. We need to know the stoichiometry of the reaction. If we write this reaction, we find out that when we write a balanced reaction, we see it's a 1-to-1 reaction between nitric acid and potassium hydroxide to produce potassium nitrate and water. The reaction needs to go to completion. Well, this is a strong acid, strong base reaction, which we've said before, proceed essentially to 100% completion. Well, let's look and see how we would do this calculation. The number of moles of nitric acid used would be the volume of titrant of nitric acid that we used times its concentration. So this would be the number of moles of nitric acid that we delivered from the burette. The number of moles of potassium hydroxide that we titrated in the flask would be equal to the number of moles of nitric acid that we added times the fact that we know 1 mole of potassium hydroxide reacts with 1 mole of nitric acid. It's a 1-to-1 reaction. So now we've counted that there are 2.213 times 10 to the minus 3 moles of potassium hydroxide in that flask. Well, if we take that number of moles that we counted, divide by the original volume that was in the flask, we get the original concentration of potassium hydroxide. And as before, we need to be able to detect the equivalence point. So we need to know what the pH would probably be at that equivalence point. If we write the reaction once again, and remember that potassium nitrate in solution would exist as potassium ions and nitrate ions, both of which are neutral in water, we realize that the pH would be 7 because we'd have 2 neutral ions as products plus just water. So what indicators would be appropriate to use here? Well, the pH is 7, and it seems pretty straightforward what indicators we would use. We need to be a little careful here and realize exactly what's going on. In this case, the original pH in the flask is just about 13. Now we know that now because we just calculated the concentration of potassium hydroxide that was in the flask. And if you use that concentration to calculate a pH, you'd realize the pH would start out around 13. So if we look at, for example, bromethymol blue, which seems to be an appropriate indicator, we need to realize that the color changes are the opposite of what we saw in example 1. So here, the solution would probably be blue and then would turn to yellow at the equivalence point. We could also use phenolphthalein here for the same reason we could use it in the previous two examples, and that is, even though the pH 7 doesn't cut right through the middle of this color transition, the pH changes very rapidly near the equivalence point, so we might be able to get away with using phenolphthalein. Although you should note here that phenolphthalein loses a little bit of its advantage because we said before it's a lot easier to see a transition from no color to color. It doesn't hold for this transition because you'd go from a pink solution to colorless, so you'd have to decide when the pink is totally gone. It's a little harder to detect. There are a couple other indicators here that would be possible, and you could figure this out. Probably methyl red might be a candidate if the pH change was rapid enough near the equivalence point and beyond. And you can see thymol blue might work too. For our fourth and final example, let's look at a weak base, in this situation ammonia, titrated by a strong acid, in this case hydrochloric acid. So let's look at the scenario. The question asks us to calculate the pH at the equivalence point for the titration of 20 milliliters of 0.1107 molar aqueous ammonia, that's in the flask here, by 0.1400 molar hydrochloric acid in the burette. Well, what's familiar or different about this example? Well, first of all, instead of a strong base being titrated by a strong acid, as is in example 3, we have here a weak base, ammonia, being titrated by a strong acid. The concentrations used in this question should look vaguely familiar. And unlike previous examples, this example explicitly asks you to calculate the expected pH at the equivalence point of the titration. Recall that in the previous examples, we either estimated or calculated the pH at the equivalence point in order to pick out an indicator. But in this question, it just flat out asks for the pH at the equivalence point. Let's go through our familiar routine. The stoichiometry of this reaction is 1:1. HCl plus ammonia should produce ammonium chloride in water. This reaction should go to completion because the strong acid will drive the reaction with the weak base to essentially 100% completion. Well, let's look at the calculations involved here. And the calculations will be in 3 parts. First of all, we need to calculate the volume of the titrant, HCl, in the burette that will be required to reach the equivalence point. If you recall example 3 and the similarities of some of these numbers to example 3, you've probably guessed the answer is 15.81 milliliters. But let's see how we'd work through this. First question you'd ask is, how many moles of ammonia were in the flask initially? Well, that's easy. 20 milliliters times the concentration gives you 2.214 times 10 to the minus 3 moles of ammonia. How many moles of HCl would be required to exactly react with this ammonia? Well, that's pretty straightforward too. Since it's a one-to-one reaction, the number of moles of HCl from the burette should be exactly equal to the number of moles of ammonia that we started with in the flask. And finally, what volume of that 0.1400 molar HCl solution would be required to deliver 2.214 times 10 to the minus 3 moles of HCl? We can get this by taking the number of moles that we need to deliver times the reciprocal of the HCl concentration. That would leave us with liters of HCl, which we then convert to milliliters, and we'd end up with 15.81 milliliters of HCl being required from the burette. Well, let's calculate the concentration of ammonium ion in the flask at the equivalence point. Well, why would we want to do that? Well, because when this reaction is complete, the product is ammonium chloride in water. So we have ammonium ion, which is acidic, and chloride ion, which is neutral. So at the equivalence point, we actually expect this solution to be acidic because of the ammonium ion, and the total volume of that solution should be what we started with in the flask, 20, plus what we added from the burette, for a total of 35.81 milliliters of solution. So if we want to calculate the pH at the equivalence point, we need to calculate the concentration of ammonium ion at the equivalence point. That should be pretty straightforward because there should be 2.214 times 10 to the minus 3 moles of ammonium ion at the equivalence point. All the ammonia is converted to ammonium ion at that point. We divide it by the total volume at that point, and we get an ammonium ion concentration of 0.06183 molar. Well, now we can use an ice table to calculate the pH of this solution of ammonium ion. As I said, the ammonium ion is acidic in water, so it should undergo hydrolysis with water to reform a little ammonia and some hydronium ions. The Ka of this ammonium ion is 5.6 times 10 to the minus 10, and remember, you can get that by taking the Kw of water and dividing by the Kb of ammonia, which you could look up. So setting this up as an ice table and going through the usual procedures, we find that X, which will be equal to the hydronium ion concentration, will be equal to 5.884 times 10 to the minus 6 molar, which means the pH would be 5.23. And this is a general result, meaning the pH at the equivalence point should be less than 7 when a weak base is titrated by a strong acid. The actual pH will depend on the concentration of the ion involved and on the Ka value of that ion in water. So what about choosing an indicator? Well, remember the pH is 5.23 at the equivalence point. We start at a pH of around 11. That would be the pH of the 0.1107 molar solution of ammonia in the flask before any titrants added. It appears that methyl red, remember we're starting from this high pH and adding acid, would be a possible choice of an indicator. We'd see a yellow to red color change there. We might even include methyl orange or bromethymol blue if the pH change is pretty rapid near the equivalence point. We'll see these changes, these rapid changes near the equivalence point more clearly when we look at titration curves in the future lecture. So let's summarize in our 4 examples in part 1 and part 2 of the lecture, our 4 titrations. Here are the examples we covered. These aren't necessarily in order of example 1, 2, 3, and 4. I reorganized them to do some interesting comparisons. So when we titrated a strong acid by a strong base, and remember that means the strong acid is in the flask, strong base in the burette. In the flask, for the example we covered, we had perchloric acid. In the burette, we had sodium hydroxide. The products at the equivalence point, besides water, of course, would be sodium ion and perchlorate ion, which are both neutral, which left us with a pH of 7 at the equivalence point. If we had a strong base in the flask and a strong acid in the burette, and in our case, we had, for this example, potassium hydroxide in the flask and nitric acid in the burette, the products there at the equivalence point were potassium ion and nitrate ion, both neutral, so we expect a pH of 7. So these products in both of these titrations, these are strong acid, strong base reactions, do not undergo significant hydrolysis in water, and so the pH is 7. In other words, it's just determined, the pH is determined by the autoionization of water. If instead we had a weak acid being titrated by a strong base, and in our example the weak acid was acetic acid, titrated by the strong base sodium hydroxide, the products at the equivalence point were sodium ion and acetate ion. Sodium ion was neutral. Acetate ion, on the other hand, was basic, and so we had a pH of greater than 7 at the equivalence point. For a weak base titrated by a strong acid, our weak base in our example was aqueous solution of ammonia, titrated by the strong acid hydrochloric acid. The products at the equivalence point were ammonium ion, which is acidic in water, chloride, which is neutral, so we expect the pH to be less than 7 at the equivalence point. In these final 2 cases, the products at the equivalence point, or I should say at least one of them in this case, could undergo significant hydrolysis in water. So the pH is determined by these hydrolysis reactions, hydrolysis in this case of acetate, in this case of ammonium ion, and not simply by the autoionization of water. Now we should keep in mind that even in these last 2 cases where the pH is greater or less than 7 at the equivalence point, the autoionization of water is still occurring, but its contribution to the hydroxide and hydrogen ion concentration, and thus the pH, is insignificant in comparison, at least in most of the cases we'll look at. A couple of examples we did not cover, and this was intentional, was a weak acid titrated by a weak base. An example would be acetic acid titrated by ammonia, or a weak base titrated by a weak acid. An example could be the methylamine, which is a weak base, titrated by nitrous acid, which is a weak acid. In these two examples, these weak acid, weak base reactions, they generally do not go to 100% completion, and so therefore, at least for our purposes, they're not ideal for titrations where we would want quantitative information.